Okay, as promised, now we're talking about modeling with exponential functions. This is still 1.4. And our objective here is to interpret and apply these exponential function models. So these are actually very common and one of the more versatile tools that we have in our toolbox. So why do we use exponential functions? First of all, their behavior is very predictable. So very easy to apply. They're easy to calculate. Exponential equations are easy to solve. And best of all, they work, as long as you restrict the domain. So let's talk about some applications. For instance, population growth. This applies in terms in biology with the growth of a sample of population, a culture, and infectious diseases. It also applies in human geography in analyzing demographics and how populations grow in the real world. So the one model that we're going to be using here is something called the Malthusian Model, named for a now infamous, I guess he was an economist, Malthus. He proposed that the world population was growing exponentially, which he modeled, and also proposed that to counteract that and to make sure that everyone has enough supplies to live, that a certain amount of people should be designated for slaughter. So not great ideas there, but at least he gave us this model. All right, so as an example, we're going to talk about how this specifically applies to cultures of bacteria. So in this case, we have a culture of Giardia lambda, where the population P given in colony forming units per milliliter as a function of time in hours. And this model specifically is P of T is 37 times 1.3 raised to the T power. So why is this an exponential model? So ultimately what we have here is we have some constant in front, right? Which we will figure out quickly is the initial population. The 1.3 is called the growth rate. And of course, T is the variable, okay? So some things to note here. P of 0, right, is 37 times 1.3 to the 0 power, which is equal to 37. And the way to interpret this is 37 then represents the population at time t equals 0. So it's a starting point, right? All right, so question. Find the population after 4 hours. Well, 4 hours tells us the time. So we're actually going to evaluate P at 4, which is 37 times 1.3 raised to the 4 power, which equals 37 times 2 times 85, 61. And this is approximately 105.68. Okay, so in the span of 4 hours, we go from 37 colony forming units per milliliter to 105.68. And using the tools of the next section, we'll be able to figure out questions like, when will the population break 500 colony forming units per milliliter? Can't do that yet. Patience. Of course, this applies also to questions of human population growth, right? So we have a table of the U.S. population between 1960 and 2010. So our year, our population, and this is in millions. So we've got 1960, 179 million, 1970, 203, 1980, there are now 227 million, in 1990, you've got 250, in 2000, you got 281, and by, I ran out of room here, sorry, 2010, you now have 310 million people. Okay, so we're going to plot these values and fit an exponential curve. So it's appropriate to use an exponential curve here because, one, it'll fit the data pretty well, but also when we're looking at a limited time frame, it actually works pretty well to extrapolate a little bit beyond the years that are specified here. So we'll think of this in terms of not the actual years necessarily, but we'll think about it in terms of years since 1960. Okay, so really what we're talking about here is essentially we suspect that P of t is the amount of people at the very beginning, 179, times some base, some growth rate raised to the t power. So this is what we're going to try to fit, and then we'll estimate what b might be using some of these table values. So first let's graph this. Okay, so we're looking at increments of 10 years. So here's 10, 20, 30, 40, and 50. And since we're looking at values that are much greater than 0, we're going to actually break our y-axis here so that we can start at a reasonable starting point. So let's call this 180. And then 200, 220. Is that going to be enough room? Maybe let's go by 30s. Let's go by 30s. So it's going to be 210, 240, 270, 300, and 330. Okay, that's better. So our individual discrete data points, remember, we start at 0 with 179, which is like right there. And then at the 10-year mark, which is 1970, we go up to 203. That's roughly here. Maybe a little bit closer to the 210 mark. At 20, we hit 227, just right around here. At the 30 mark, we hit 250, right around here. 2000, which is the 40 mark, 281. And lastly, in 2010, we hit 310. So you can imagine, this looks like a straight line, but it probably fits something more like this, which curls upward and is not a straight line. And it fits pretty well for this range of values. Okay, so using this, we can estimate, for instance, the population in 1985, or we can extrapolate to 2020. Another use of this class of functions, family of functions, is radioactive decay. So this uses a decaying model now, where I'm maybe more interested now instead in we'll talk about it in more detail later because we actually have to model this pretty detailed. But essentially, you have some unstable material with a given mass at time t. Mass is usually in grams or milligrams. And it decays, meaning it, as time goes on, there's less and less of it. Specifically here, in the example that we're talking about here, they have the half-life of an element called bismuth. Whoops, that's not how you spell that. Bismuth 210 being 5 days. So the way you want to think about this is, if the initial amount is 300 milligrams, then we can think about the amount of bismuth 210, its mass, in terms of this table. So we have, T in days, and the mass in milligrams. So on day 0, so at the starting point, we have 300. On the start of the 5th day, we have half of the initial amount, or half of the amount in the previous 5-day block, at the start of the previous 5-day block. Then at the 10-day mark, we again have half of that. So this would be 75. At the 15-day mark, half of that, which should be, what would that be? 37.5, and so on. So as we can see, the half-life is representing a radioactive decay model. So our model will look like m of t equals the initial amount times b raised to the t power, where the initial amount was given to us, 300, and m of 5 equals 150. So using the tools of the next section, we're going to be able to figure out what is that decay rate. And we'll need logarithms to do this.